The summer of 2002 was hot in India. It was the kind of heat that sits heavy on the chest. The streets of Kanpur were dusty and bright. Kanpur is a major city in the northern Indian state of Uttar Pradesh. Most students at the Indian Institute of Technology had gone home. The campus was quiet. The hostels were empty. But in one office, the air was electric. 3 people sat in this office. It belonged to a professor of computer science and engineering named Manindra Agrawal. The other 2 were students. They were 21 years old. Their names were Neeraj Kayal and Nitin Saxena. They were staring at a whiteboard. They were looking for something that did not exist. For centuries, mathematicians had hunted for a specific treasure. They wanted a better way to test if a number was prime. This sounds simple. You learn about prime numbers in grade school. They are the atoms of math. They are numbers like 7 or 11. You cannot divide them by anything except 1 in themselves. Small primes are easy to spot. You can see that 13 is prime, but what if the number is huge? What if it has 300 digits? The best minds in history had tried to find a fast and perfect test. For centuries, this question haunted the greatest minds in history. The ancient Greeks wondered about it. The French genius Pierre de Fermat wrestled with it. The German giant Carl Friedrich Gauss searched for a pattern in the primes. They all found partial answers. They found methods that worked most of the time. They found methods that worked slowly, but no one could find a method that was fast, perfect, and worked for every single number. The 3 men in Kanpur did not care about history. They cared about algebra. They believed the answer was simple. They believed the world was wrong. On a quiet morning in July, they found it. They wrote a paper on it, only a few pages long. They sent it to the internet. The next day, the world of mathematics woke up to a shock. A boy from a modest home in Prayagraj had just helped solve a riddle that had lasted 2,000 years. How did he do it? Nitin Saxena grew up in the city of Prayagraj. It is a city of rivers in northern India. 2 major Indian rivers, the Ganges and the Yamuna, meet there. Pilgrims come from all over India to bathe in the water. It is a place of faith and history. Nitin Saxena was born in this city on the 3rd of May, 1981. The India of the early 1980s was a different place. The economy was closed. The internet did not exist. For a middle-class family in a town like Allahabad, life was slow and steady. Resources were scarce. Ambition was the only currency that mattered. Nitin was not interested in history. He was a quiet boy. He lived with his family in a simple home. They were not rich. They were a typical middle-class family. His parents valued education. In India, education is the only ladder that matters. Nitin went to boys' high school. He sat in the back of the class. He listened to the teacher drone on about geography. He looked at the maps. He looked at the dates of wars. He felt bored. The problem was the words. Subjects like history required essays. You had to write long paragraphs. You had to describe things. You had to use adjectives. Nitin felt this was a waste of time. Why write a page when a sentence would do? Why write a sentence when a symbol would do? Then he found algebra. It happened in the 8th grade. Most students hate the moment when math stops using numbers. They hate when X and Y appear. Nitin felt a spark. He called it romantic. Algebra was clean. It was pure logic. You have an equation. You move the parts around. You follow the rules. If you do it right, the answer appears. It is not an opinion. It is the truth. Fascinated by the symbols, he immersed himself in the lives of renowned scientists. He viewed these figures as true explorers, not merely completing academic assignments, but actively charting the universe. He decided to become one of them. He stopped caring about the subjects that bored him. He focused only on physics and math. This led him to prepare for the hardest exam in the country. The entrance exam for the Indian Institute of Technology is brutal. With an acceptance rate lower than Harvard's, this highly competitive exam is known as the IIT Joint Entrance Exam, attempted by millions, yet only a few thousand succeed. It is a grueling test of physics, chemistry, and math. It breaks many students. In 1998, Nitin secured a high rank. He won a ticket to the most prestigious program in the country. He joined the Computer Science and Engineering department at IIT Kanpur. He was 17 years old. He was leaving home for the first time. He was walking into a place that would change his life. The Indian Institute of Technology Kanpur is an island. It sits about 10 miles away from the chaos of Kanpur city. The campus is a lush green forest that spans 1,000 acres. Peacocks roam the lawns. The architecture is modern and stark. It was built in the 1960s with help from American universities like Princeton and MIT. It was designed to be a temple of science. When Nitin arrived, the computer science department was buzzing with energy. It was the golden age of the dot-com boom. The internet was changing the world. Everyone wanted to write code. Everyone wanted to join a startup in Silicon Valley. But Nitin was different. He was not interested in writing code for a website. He was interested in the deep theory. He was interested in the math that made the code possible. He met two people who would become central to his story. The first was Neeraj Kayal. Neeraj was a batchmate. He was also brilliant and driven. He and Nitin shared a similar wavelength. They did not need to speak much to understand each other. They could sit in silence and work on a problem for hours. The second person was Manindra Agrawal. Manindra was a professor in the department. He was an alumnus of the institute. He had come to IIT Kanpur as a student in 1982 and never really left. He was a quiet man. He was introverted. He did not care for the rat race of publishing papers just to get tenure. He cared about hard problems. Professor Agrawal had a unique philosophy. He believed in the power of the undergraduate mind. In most universities, serious research is reserved for PhD students. Professors think that undergraduates do not know enough. They think they need to read hundreds of papers before they can start. Agrawal disagreed. He believed that knowing too much could be a trap. If you read every paper, you learn what is impossible. You learn from the failures of the past. You get scared. Agrawal wanted students who were fresh. He wanted students who did not know that the problem was supposed to be impossible. He found Nitin and Neeraj. The three of them formed a team. It was an informal group. They met in Agrawal's office. They drank tea. They stared at the whiteboards. They did not have millions of dollars in funding. They did not have a massive lab. They had paper and pencils. They had their brains. A prime number is an integer greater than 1 that has no factors other than 1 and itself. The numbers 2, 3, 5, and 7 are prime. The number 4 is not prime because it is 2 times 2. Primes are the building blocks of arithmetic. Every number is made of primes. The number 12 is made of 2 times 2 times 3. The ancient Greeks knew that there were infinitely many primes. Euclid proved it over 2,000 years ago. Every time you buy something online, you use prime numbers. Your bank uses them. The army uses them. This reliance is based on a simple fact. It is easy to multiply two prime numbers. It is very hard to pull them apart. The problem of checking if a number is prime is called primality testing. If I give you the number 17, you can check it in your head. You try dividing it by 2. You try 3. You try 5. None of them works. You say it is prime. But what if I give you a number with 500 digits? If you try to divide it by every number up to its square root, the sun will burn out before you finish. The universe will end before your computer gives you an answer. The security of these cryptographic locks hinges on a test that requires finding extremely large prime numbers. The process involves selecting a random number and then asking a fundamental question: is this number prime? By the year 2002, mathematicians had developed clever ways to cheat. They had created probabilistic tests. The most famous was the Miller-Rabin test. These algorithms were fast. They could take a giant number and give you an answer in milliseconds. But there was a catch. The answer was not always certain. If the Miller-Rabin test said a number was composite, it was definitely composite. But if it said the number was prime, it was only probably prime. The chance of error was tiny. It was smaller than the chance of your computer being hit by a meteor, but it was not zero. For engineers, this was good enough. But for mathematicians, it was an itch that could not be scratched. Mathematics is the search for absolute truth. Probably is not the truth. There was another class of tests. These were deterministic. They gave a definite yes or no answer, but they were slow. They worked for many numbers. But no one could prove that they worked quickly for all numbers. There was a dream. The dream was to find an algorithm that had three properties. First, it had to be general. It had to work for any number. Second, it had to be deterministic. It had to be 100% correct every time. Third, it had to be polynomial-time. This means it had to be fast. As the number got bigger, the time taken should grow slowly. This was known as the primes in P problem. P stands for polynomial time. It is the class of problems that computers can solve efficiently. Many experts believed that primes were in P, but no one could prove it. They were stuck. They had been stuck for decades. Nitin met Manindra Agrawal at IIT Kanpur. Agrawal was a professor who liked hard problems. Nitin needed a project to graduate. He teamed up with his friend Niraj Kayal. They went to Agrawal. They were asked to work on the prime problem. Agrawal had a hunch. He had an idea about polynomials. A polynomial is an expression like x plus 1. Agrawal believed that prime numbers behave differently when you put them inside these expressions. He thought he saw a pattern. They started with a simple idea. It is a version of Fermat's little theorem. Take a number n and another number a. Look at the expression x plus a to the power n. If you expand this expression, you get a long string of terms. If n is prime, then this long string has a special property. If you divide it by n, it looks exactly like x to the power n plus a. This is a beautiful fact. It is always true for primes. The problem is that checking this expression is too slow. It has too many terms. It takes too long. So the trio tried to simplify it. They decided to do the division not just by the number n but also by a polynomial x to the power r1. This reduced the number of terms. It made the calculation fast. But there was a danger. When you simplify the test, you might lose accuracy. Maybe some composite numbers would pass the simplified test. Maybe they would disguise themselves as primes. The challenge was to find a way to make sure that no composite number could hide. They needed to find the right value for r. They needed to check just enough values of a. They worked on this for a year. They had ups and downs. They thought they had solved it, only to find a mistake. They hit dead ends. They spent long nights in the lab. Most students would have given up. They had exams. They had careers to think about. But Nitin was possessed by the problem. He was stubborn. He wanted to know why the math behaved the way it did. Winter gave way to spring, and Nitin completed his degree. He was faced with a choice: take a job and earn an income, or stay and tackle the unsolved problem with no guarantee of finding a solution. He chose the latter. He remained in Kanpur, enrolling in a doctoral program, dedicating himself to solving the enduring problem. The breakthrough came in the summer of 2002. The heat was terrible. The monsoon rains were pounding the roof. The three men were tired, but Agrawal had a new thought. He looked at the polynomial equation again. He realized they did not need to check every number. They only needed to check a small set of numbers. If the rule worked for a few specific values, it had to work for everything. They looked at the math. It held up. They looked for the error, but there was no error. The proof was elegant. It was short. Their original draft was less than 10 pages long. It did not require new math. It used math that had been known for 100 years. It was just that no one had ever put the pieces together in this way. They titled the paper "Primes is in P." In early August 2002, Agrawal emailed the paper to a few top experts. One was Shafi Goldwasser at MIT. Another was Carl Pomerantz at Bell Labs. Experts in prime around the world downloaded the file. They expected to find a mistake. They read it. They reread it. Carl Pomerantz said, "This algorithm is beautiful." Shafi Goldwasser called it the best result I've heard in over 10 years. The news traveled at the speed of the internet. It jumped from email to email. It crossed oceans. On the 8th of August 2002, the New York Times ran a story. The headline read, "New Method Said to Solve Key Problem in Math." The server at IIT Kanpur had crashed. Mathematicians around the world were downloading the paper. They could not believe it. They checked the lines. They looked for the mistake. They found none. The boys from the small town of Kanpur had done it. They had proven that you can test for primes quickly and perfectly. The algorithm became known as the AKS Primality test. The A stood for Agrawal, the K for Kale, the S for Saxena. It was the first algorithm in history to be general, deterministic, and polynomial-time and unconditional. It checked all the boxes. It was perfect. Nitin Saxena went from being an unknown student to a celebrity in science. Nitin could have coasted. He could have spent the rest of his life talking about that one summer. But Nitin Saxena was a scientist. The solution was done. The thrill was gone. He wanted a new problem. The awards began to pour in. In 2006, the trio won the Gödel Prize. This is the Nobel Prize of Theoretical Computer Science. Nitin was the youngest person ever to win it. He was barely 25. They won the Fulkerson Prize. IIT Kanpur gave Nitin the Distinguished Alumnus Award. The world wanted to know who this young man was. They found Nitin was quiet and humble. He smiled shyly at the cameras. When asked about the discovery, he deflected the praise. He talked about the team. He talked about the fun of solving the puzzle. He did not speak of conquering the mountain. He spoke of understanding it. He stayed at IIT Kanpur to finish his PhD. He could have gone to Harvard or Stanford. He chose to stay with Agrawal. He remained loyal to the soil that grew him. His PhD thesis was titled Morphisms of Rings and Applications to Complexity. It was a deep dive into the algebra that had powered the AKS result. But Nitin knew that he could not stay in the glow of one success forever. In science, you are only as good as your next problem. He needed to grow. He needed to see the world. He left India. He became a wandering scholar. He spent time at Princeton University. He walked the halls where Einstein had thought about relativity. He absorbed the intense culture of American research. He went to the National University of Singapore. He moved to Europe. He joined CWI Amsterdam in the Netherlands. This is a famous center for math. It is where the Python coding language was born. In 2008, he moved to Germany. He became a Bonn Junior Fellow at the University of Bonn. This was a big honor. It gave him the freedom to run his own research group. He spent 5 years in Germany. He matured. He was a leader. He guided PhD students of his own. He published papers on new topics. He began looking at problems even harder than primality. Nitin's field is called computational complexity. It is the study of how hard problems are. Imagine a landscape of problems. In the valley, you have the easy problems. These are problems like adding numbers or sorting a list. These are in class P. On the mountain, you have the hard problems. These are problems like the traveling salesman problem. These are in class NP. The biggest question in math is P versus NP. It asks if the hard problems are actually easy in disguise. Most people think they are not, but no one knows for sure. Nitin works on a specific part of this map. He works on algebraic complexity. He looks at polynomials. He asks questions like, how many operations do I need to calculate this formula? He studies a class called VP and a class called VNP. VP is the algebraic version of easy. VNP is the algebraic version of hard. Nitin wants to prove that VNP is different from VP. He wants to prove that some algebraic problems are truly impossible to solve quickly. This is deep, abstract work. It does not make headlines like primality testing. It is the slow, hard work of laying the foundation. One of his big ideas is the border. In math, you can sometimes get very close to a solution without touching it. You can approximate it. This is the border. Nitin asks, if I can approximate a solution, does that mean I can find the exact solution? He has shown that in many cases the answer is yes. He has demystified the border. He has shown that the fuzzy edge of the map is not so scary. This work helps us understand the limits of computation. It tells us what computers can do and what they can never do. In 2013, Nitin returned home to India. He accepted a position as a professor at IIT Kanpur. It was a full circle. The boy who had learned algebra in the classrooms was now teaching in them. He settled back into the rhythm of the campus. He took long walks. He mentored students. He became the N. Rama Rao Chair Professor. But he also began to look outward. He saw that the world was changing again. Artificial intelligence was rising. Algorithms were no longer just solving math problems. They were driving cars. They were writing poetry. They were diagnosing diseases. Nitin realized that India needed to lead in this new world. In 2022, he became the founding coordinator of the Center for Developing Intelligent Systems. In 2025, he took on a bigger role. He became the founding dean of the Wadhwani School of AI and Intelligent Systems at IIT Kanpur. This is a new challenge. He is no longer just a solver of problems. He is a builder of institutions. He has a clear vision. He does not just want to copy what Silicon Valley is doing. He wants to build AI that matters for India. He talks about AI product development for the local economy. He wants to use high-tech to solve low-tech problems. He wants to help the farmer and the shopkeeper. He believes that the abstract math he loves can have concrete benefits for the common man. He is also a voice of reason. In a world of hype about AI, he looks at the foundations. He asks the hard questions about what these systems can actually learn. He uses his background in complexity to analyze the limits of AI. Nitin Saxena today is a man at the height of his powers. He is still young in the world of math. He is a private person. He lists his interests simply. He likes fixing electronics. He has a philosophy of simplicity. When he advises students, he tells them to look for the why. He tells them not to be intimidated by the experts. Sometimes experts are wrong. Sometimes the impossible is just a lack of imagination. He is a living proof that you do not need to be born with a silver spoon to change the world. You do not need a famous last name. You do not need to be in New York or London. You just need a clear mind. You need a good teacher. You need a friend to work with. And you need the courage to ask a question.